This is Euclid Book 3, proposition number 37, and what we're going to do here is we're going to finish out our final proof. Next time I'm going to have a video on Book 4, and we've got a circle here. It is A, B, C, and of course goes through E here, and then we got a bunch of lines. And line DB passes through circle ABC, but it doesn't cut it. We also have a line from point D to point C to point A. We have another line that goes from point D to point F, which happens to be the center of the circle. You say, well, how do we find the center of the circle? We found the center of the circle because we used Euclid Book 3, proposition number 1. Then we drew a line from point D to point E, and this DE line here touches circle ABC at point E. Anyway, we have also drawn a line from the center of the circle, which is at point F, to point E. Center F, outermost E. Okay. Now, we are going to say as a given that the rectangle that you could form from lines AD and DC, this is DC right here, DC, and here's AD here. If you were to form a rectangle from those two lines, the area inside that rectangle would be equal to the area that you would form if you formed a square using the line DB. Okay, if you formed a four-sided square using the line DB as one of the four sides, okay, then the area inside that square would be the same as the area of the rectangle ADDC, which I just showed you a minute ago. All right. Now what we're trying to do is we're trying to prove that line DB, this line DB here, touches circle ABC. How are we going to do that? Well, because DE touches ABC, here's DE and it touches ABC, we've already established that F is the center of the circle, then we can say that angle DEF is a right angle. And we can do that by Euclid Book 3, proposition number 18. Now we can also say that the rectangle formed by ADDC, well, where's AD? Here's AD here, and here's DC here, the rectangle formed by those two lines there, the area inside of it would be equal to the area inside of the square of DE. Okay, so we'd form a square, and one of the sides of that square would be the length of DE. So the area of ADDC is equal to the area of the square of DE. And this is by Euclid Book 3, proposition number 36. We already said earlier that the area of ADDC is equal to the square of DB. That means that the square of DB and the square of DE are equal areas. And if they're equal areas, then that means that the length of DB and the length of DE are exactly the same. Now we can also go on to say that the length of FB here and the length of FE here are exactly the same because of all radii of a circle are equal. And then if we go one step further, we can say that the length of FD is equal to itself. Well, we have three sides equal to three sides here. These two triangles, triangle DEF and triangle DBF, are exactly the same size. And because of that, angle DEF, which this is D, this is E, this is F, is equal to DBF, DBF. Okay, we can say that by Euclid Book 1, proposition number 8. Now we already established that angle DEF is 90 degrees. Now we can go on to say that angle DBF is 90 degrees. Okay? Now, if we were to take line FD and produce it further out, we could have a diameter of a circle. That's just a fact. Alright, so the final piece of this proof is straight lines drawn at right angles to the diameter of a circle from an extremity touches the circle. Alright? This is a straight line, okay? And it has been drawn at right angles to the diameter of a circle. So therefore, this straight line touches the circle. And we can prove this by Euclid Book 3, proposition number 16. Alright, now I know there's a little bit more to this proof, but I'm going to leave that up to you. If you want to post it as a video response, you go right ahead. I'd love it. Talk to you later. Tell you more in a future video. Stay tuned.